Welcome. Today's topic is also the mechanical properties of ceramic materials, which we have been continuing for the last couple of lectures. In an earlier lecture, we have already discussed the different mechanisms of toughening ceramic materials, whether it is by fiber reinforcement or whisker reinforcement or simply by transformation toughening. Today, we look at it some of the implications of this transformation toughening or the toughening in general, and for that we will discuss what we call the R-curve behavior of ceramic materials in particular. It comes from the Irwin's analysis of fracture mechanics, where he has calculated the or postulated the crack extension resistance curve. Okay. So, there is a extension when the crack starts propagating, a resistance is also created, and that is what the term says, the crack extension resistance curve or simply the R curve. What are its implications or characteristics? It refers to a situation where fracture toughness KIC, which we have discussed earlier, we have defined fracture toughness, we have also discussed how to measure the fracture toughness of ceramic materials by different techniques. So, this fracture toughness property of ceramic material increases with increasing size of the crack. Okay. So, that is the basic premises on which this R-curve behavior has been discussed or will be discussed now. So, by toughening we actually see that the toughness value or the fracture toughness value KIC is increasing with increasing size of the crack. So, that is the primary characteristic of a R-curve behavior so far the mechanical property of ceramics is concerned. This is in contrast to the normal ceramic material, well, which are not toughened, which do not get toughened either by a fiber reinforcement or crack deflection or transformation toughening. So, normal ceramic material do not have these characteristics. So, their KIC value, the fracture toughness, is independent of flaw size. So, that is the basic difference between the normal behavior of a ceramic material and the R-curve behavior of the ceramics, which have been toughened by some means. R-curve behavior is an important consequence of the toughening mechanism discussed previously, that we have just discussed. We have just mentioned that primarily this behavior is observed where this ceramic materials have been toughened by some mechanisms which we have discussed. This is a typical behavior of R-curve behavior or comparison of two different classes of ceramic material. One is the R-curve materials having the R-curve behavior and materials which do not have that. If you plot KIC of these two groups of materials as a function of flaw size, the C, which we have discussed in details earlier. So, for the materials which do not show the R-curve behavior, the KIC value is more or less independent of the flaw size. Okay. Whereas, if you have a R-curve behavior materials or R-curve materials which show R-curve, the R-curve is like this, that the fracture toughness actually increases with the flaw size. Of course, it does not increase continuously, initially increases and then there is a kind of steady state is reached between the propagation of the cracks and the strengthening mechanism. So, at a certain stage it becomes more or less constant once again. Well, some more observations on this. Crack breaching and transformation toughening are the major causes of this behavior, which we have just mentioned also. And the crack closure stresses are imposed either by breaching ligaments or the transformed zone ahead of the crack tip. If we remember how exactly the toughening takes place, either by the transformation mechanism or transformation toughening, that means the materials ahead of the crack tip, they get transformed and form a compressive load or compressive stress, which does not allow the crack to further propagate. So, the energy is basically get absorbed by this transformation mechanism or transformation toughening. Similarly, if you have a large number of fibers in the front of the crack tip, then these fibers also act as a anchoring of these fibers, and the crack cannot expand or cannot propagate in the forward direction. So, that is how the toughening is increased as the crack tries to propagate further. The fracture toughness, however, does not increase, as also I mentioned a few minutes back, does not increase indefinitely, but reach more or less a constant value when a steady state is reached, as the ligaments tend to break and pull out. So, after some time, of course, the stress builds up and the ligaments either gets or the fibers gets broken, or it can be there is a debonding also takes place. Compared to the KIC value, the fracture toughness, the strength, if you measure the strength of these materials, they have a different characteristics against flaw size. For normal ceramics, which do not show the R-curve behavior, the strength decreases. Strength decreases initially quite rapidly as the flaw size increases, and then at a larger flaw size it more or less becomes constant. That is the characteristics of the normal ceramic materials without having the R-curve behavior. However, if the materials having R-curve behavior, that means the materials which have been toughened already and KIC value is higher, you have a higher strength, not only higher strength, but also the decrease is rather low, and it comes to a constant value at a much higher level of strength. So, strength increases by the toughening also, but as a flaw size it does not, the strength is the reverse of that. KIC increases, whereas strength decreases. Implications of R-curve behavior. Degradation in strength is less severe in ceramics with R-curve behavior, as we have just observed in the earlier diagram. So, degradation as it is strengthened, as it is the toughened. So, the degradation in strength is less severe in ceramics with R-curve behavior. That is one implication of R-curve. So, the reliability of the ceramics also improves. That means, one of the major problems of ceramic materials is unreliability of the property, particularly the mechanical property, because of the fracture toughness, because of the brittle character. Once the crack propagates, it has a tendency to propagate at very fast rate, almost a catastrophic failure takes place. So, it completely depends on what kind of cracks are already present there, or whether we can arrest those cracks by some means like toughening mechanism and so on. So, there is always the reliability problem is there with ceramic materials, and that is one of the major weaknesses of all ceramic materials in general. However, once the toughening is done by one mechanism or the other, the reliability improves, and therefore, the toughening is also related to the R-curve behavior, and therefore, R-curve behavior or the materials showing R-curve behavior are supposed to be more reliable than the normal materials. However, there is a notion, there is a proposition, or there has been some observations by researchers that the materials which show R-curve behavior normally are prone to fatigue failure. Well, fatigue failure is basically a cyclic loading. We will mention briefly about what is the fatigue later on, but so far we are discussing about the strength. Strength certainly is becomes more reliable, the materials becomes less prone to fracture, however, under normal stress condition, but if there is a fatigue loading or the cyclic loading, a kind of cyclic loading of tensile load as well as compressive load one after the other, then there may be a possibility of failure or less less reliable it becomes, particularly under fatigue loading. There is also a proposition, or there is also some observations that the materials which behave or show R-curve behavior improves their thermal shock resistance. In general, as you know, because of the less thermal conductivity of ceramic materials and poor fracture mechanical properties, ceramic materials have less shock resistance, but the materials who have R-curve behavior or toughened material do improve the thermal shock resistance, which is kind of expected of these behavior of this kind of improved material or properties with improved the materials with improved properties. Okay. So, that is all about our knowledge of R-curve behavior materials, and that, as you have seen, is quite closely related to the toughening or toughened ceramics. Then we come to another aspect of mechanical behavior of ceramic materials, that is what we call the Weibull distribution. Now, as has been mentioned time and again, that the reliability of the ceramic materials, so far as the mechanical properties are concerned, are quite poor, and some material may fail suddenly. The same material, more or less prepared in the same manner, may not fail. Okay. So, it is difficult to predict the behavior in that manner. So, in that context, a statistical distribution of these measurements have been proposed, and that is very important for ceramic materials where the reliability is an issue. As the ceramic materials are known for their brittle fracture without appreciable plastic deformation, that is the definition of brittle fracture, the uncertainty of measurement is appreciably high. Okay. That is quite obvious. In order to arrive at a reliable strength value, statistical analysis of data is very, very important. Okay. So, first of all, we have mentioned earlier also that the number of data points, the number of measurements must be quite high, so that we can get a statistical average and reliable data. The most widely used statistical approach is a semi-empirical function known as Weibull distribution function. So, Weibull distribution function is a semi-empirical function which is normally used to analyze the reliability of the data points and the reliability of the properties as such. This function, which is mathematically represented as f x equal to m x m minus 1 exponential minus x to the power m. So, that is the function, Weibull function, where f x is a frequency distribution of random variables x and m is a shape factor, usually referred to as Weibull modulus. Okay. So, in this function m is a very important parameter for our consideration. We will see how this what is the consequence or what is the implications of this Weibull modulus. If you plot this function as a function of a particular parameter, stress parameter sigma by sigma 0, which is becomes x actually. If you take this as x, so f x by f x against x, x can be has been taken as sigma by sigma 0. So, this bell shaped curve, a Gaussian distribution curve, can be seen, and the distribution function for which x has been taken as the sigma by sigma 0, as I just mentioned, where sigma is the failure stress and sigma 0 is some normalizing parameter. Okay. Sigma 0 is also a stress of under certain specific condition. We will see what is that specific condition. So, it is a kind of normalized stress condition. So, we are plotting f x as a function of normalized stress, fracture failure stress, normalized failure stress actually. So, if you take large number of samples, you find out what is the failure strength of that particular sample, and then plot that as a function of f x. So, it is a bell shaped curve or a Gaussian distribution curve is obtained, and the shape of the curve changes with the different values of m. Okay. So, depending on the either you can say depending on the shape of the curve the m is determined, or for different values of m the shape changes. As you can see from this plot, if the m is low, it is more a broad peak with a broad peak with a less defined peak, whereas if m increases, m value of m increases, if a much better defined peak and a narrow peak, or half width is less in case of m having higher values. So, that is also a very important observation. The survival probability, that is the fraction of samples that would survive at a given stress level, we have said sigma is actually the failure stress. So, at that any particular level, what is the survival, either it will break or it will remain intact, that is the condition. So, the survival probability can be defined by this function, again the fraction of samples that would survive at a particular given stress level may be expressed as this integration x to infinity f x dx. That is what we can say is the survival probability. That means, basically it is the area under the curve within a particular range, x to infinity. Okay. Replacing x by sigma 0, which you have done earlier. So, you get s sigma by sigma 0 f sigma by sigma 0 d sigma by sigma 0, and by integration you can get this solution, that is exponential minus sigma by sigma 0 all to the power m. Okay. And that is the Weibull modulus here, and if you take a logarithm of that, and in fact double logarithm, and then take an inverse of this, because there is a x here, a minus here, exponential minus. So, you will get a relationship like this, m ln sigma by sigma 0 equal to m ln sigma minus m ln sigma naught, okay, or sigma 0. So, this expression it becomes a linear relationship. So, if you plot this item against ln sigma, you will get a straight line. So, that is what has been shown here. This is a minus double logarithm of 1 by s as a function of ln sigma. You will get a negative straight line with a negative slope, and that slope is actually equal to m, okay, m the Weibull modulus. So, the plot of minus ln 1 by s versus ln sigma would give a straight line plot with a negative slope of minus m, which is nothing but the Weibull modulus, and sigma 0 can be obtained from the intercept of the on the vertical axis. If you go back to this equation, so the sigma 0 here will be the intercept, m ln sigma will be sigma 0 will be the intercept. So, from this intercept one can calculate sigma 0, okay, and from the slope one can get the Weibull modulus. Now, the physical significance of sigma 0, it is the stress at which the probability of survival of the specimen is equal to 1 by E or 0.37. So, sigma 0 actually a constant with respect to those that particular experiment. So, it refers to the probability of survival of the specimens equal to so many specimens will survive at sigma 0, okay, and with respect to that sigma you have to measure, or you have to get the ratio of that. So, the physical significance, so it is a constant value that in that manner, and you can get what is that value. So, a few comments on m. The most important parameter out of this statistical analysis is the modulus or the Weibull modulus m. It should be remember that the Weibull modulus m is no way a measure of the strength. It is not a strength. Sigma is the actual strength, or that the fracture strength with different samples, and the modulus is not a strength here, right, unlike the modulus of rupture and so on. Modulus of rupture, which we have discussed earlier, MOR, is certainly a actual strength of the material, but m is not a measure of the strength. It is only a measure of the extent of the uniformity or the repeatability of the measured values of the mechanical property. Okay. So, if the measured property, a large number, as you have mentioned, when you are trying to get a reliable mechanical property data, you have to use a large number of samples, large number of data points, and how reliable those data points, that actually is the measure, or m is the measure of that. So, higher is the value of m, higher is the reliability factor, that means higher is the reproducibility between the samples. So, the samples are more uniform, or they have a uniform microstructure, uniform grain size, uniform homogeneity, and so on and so forth. So, it is always better to have higher m value, so that the measure, not only the measurements are more reliable, but the material will behave under service as a reliable material. So, our objective must be to get as much value of m, or the Weibull modulus, as possible for a particular set of data. Yeah, higher is the value of m, better is the uniformity of the flaws, crack size present in the material, right. So, because statistically particular material may have a large size, different sizes of flaws, and if the flaw size are different in any particular sample or a set of sample, obviously the measurement will be widespread, or the values we will get will be widespread, and Young's modulus the Weibull modulus will be small or smaller value. Whereas, if you have a better homogeneity, crack size are uniform in this material, grain sizes are uniform, or you have even chemical homogeneity, phase distributions are uniform. Even when we are using a toughened material, if the toughness is uniformly distributed over this whole sample, volume of the sample, then we will have a higher Weibull modulus. So, our approach must be to get as high Weibull modulus as possible. As M is not a measure of the material strength, a weak material may even possess a very high value of M, as long as the variation of the properties, the variation of the strength is not large between the different measurements or between the different samples of the same piece. So, a weak material may even possess a very high value of M, provided there are large but uniform size flaws in the material. It is basically a measure of the uniformity of the microstructure, which may include flaws, grain size, and the overall homogeneity of the sample. So, it is the reliability or the reproducibility of the measurements which actually gives you a higher value of modulus. It should also be remembered that the parameter M is determined based on a statistical distribution of the experimental results, and therefore, for better accuracy it is necessary to acquire as many data as possible. I mean, normal suggested figure is more than 100. So, if you really want to measure the accurate property, particularly the mechanical property of a ceramic material, the number of points, number of measurements must be very large. Otherwise, there will be less probability of the accuracy, or the accuracy will be less, and you have problems in designing, problems of designing for a particular component or engineering component out of the ceramic materials, which we intend to do. Okay. So, that is the implications of Weibull modulus. There is one more thing to this Weibull modulus, and for which once again we use this equation which we have seen earlier. Here if S max, the probability, corresponds to sigma max, and S minimum probability to sigma minimum, if that is a kind of situation, then we can also write these equations directly from this. Ln 1 my S max is M ln sigma max by sigma 0. Okay. So, at highest sigma what is the probability, and at minimum sigma what is the probability, same thing. Okay. So, subtracting one from the other, one can get actually M, the value of M. So, the value of M actually, if you know this probability value at highest sigma max and at sigma minimum, these are the two limits, and then ln sigma max by sigma min. Okay. So, this is another expression of M, okay, which within a limit of sigma max and sigma min, minimum sigma and minimum maximum sigma. Okay. So, for any particular set of samples, the parameter the numerator is a constant, numerator of that particular equation. This particular equation is a constant, and depending only on the, of course, the number of samples n, and the denominator depends on the ratio of the sigma max to sigma mean. This denominator depends on the sigma max and sigma mean. These are the best probability values, which is proportional to sigma mean by sigma max. It is the reverse of, which means your strength or the fracture strength, maximum fracture strength what we have obtained corresponds to a crack length, minimum crack length. Okay. When the minimum crack length is minimum, that corresponds to the maximum fracture stress, whereas when the crack length is maximum, the minimum fracture stress is obtained. That is quite obvious from our earlier discussion. It is known that the materials with ARCA behavior KIC, this should be capital I, not the small I. Maybe I can change it here itself. Right, coming back. It is known that the materials with ARCA behavior, the KIC is independent of C. Okay. Without, sorry, not with ARCA, without ARCA. So, Weibull modulus does not change with increasing KIC. Once again, this should be there are some mistakes. However, for the materials which demonstrate ARCA behavior, that is toughening, in general increases the Weibull modulus, which is quite expected, right. So, having the ARCA behavior, the modulus of Weibull modulus is going to be more, and that is expected because you have the KIC is dependent on the sigma max and or the sigma, sorry, not the sigma, I am sorry, the C mean or C max, that is the crack length, and therefore, and it is a higher strength material. The ARCA behavior means it is a toughened material, and toughening has a closer distance, closer variation between sigma max and sigma mean, or the crack length of the maximum value and the minimum value is much closer, and therefore, you will have a higher Young's Weibull modulus. So, a toughened material is expected to have a much better Weibull modulus, and therefore, whenever we are looking for a reliable material, reliable ceramic material for certain structural applications, reliable structural ceramic materials, it is better to always have a toughened material either by transformation toughening or by some reinforcement of whiskers or many other different mechanisms which we have discussed. Well, that is all so far as the Weibull concept of Weibull modulus is concerned. Basically, we wanted to say that the Weibull modulus must be high enough so that the reliability of the data is much better, and we have a better material to be used for the actual applications, right. So, that is also an indication how good that material, how reliable that material will be for any technological applications or structural applications. Well, having discussed that, let us try to look at some of the extraneous factors affecting the strength of ceramics, okay. Because because of the brittleness, because of the unreliability of most of the parameters, mechanical engineering parameters. There are many different extraneous factors in addition to its basic structure, basic microstructure, and there are quite a few important parameters which also affect the strength of ceramics. The first one is of course pores. Ceramics, well, almost by definition and the way it has been prepared, we start with a large pores, large agglomeration of powders, and then we get sinter in order to achieve the higher and higher density, but it is very difficult to get the theoretical density, and therefore, there is always some amount of pores remain in any kind of ceramic material. So, pores has an important effect on the overall strength of the ceramics. The presence of pore is quite common in ceramics. They may vary in shape, size, volume as well as character. Some may be more spherical or circular in size, maybe angular in size, and there may be different shapes and sizes of pores available, and also they can be open pores or closed pores. Open pores means it is a open to the surface or interconnected pores, and closed pores means it is closed within within a single grain. So, it is an isolated pores inside the grains. Mostly the pores are at the grain boundaries, but closed pores are isolated pores and which can be within the grains. In general, pores are quite deleterious so far as the strength is concerned. They not only reduce the effective area of the solid, but also act as stress concentrators. Okay. So, although pores are really not cracks, but there are also some amount of openness within the monolithic structure of the ceramics, and therefore, the pores not only reduce the overall area through which the stress will be borne or the load will be borne, but also it can act at some under certain circumstances it can also act as stress concentrators just like cracks. Particularly when the radius of the curvature of such pores at certain points is very small and concave in nature. So, it can act as a stress concentrators, and failure will lead to that, or this will lead to the failure. Typical empirical relationship is follows as a function of pores is sigma p, the the failure stress of the material with pores as p or subscript p, then sigma 0 exponential minus b p, p sigma p and sigma 0 are volume fraction of the porosity, p is the volume fraction or the porosity, and the strength of the specimen with and without porosity. Okay. So, this is with porosity, and if there is no porosity, that would have been the failure strength sigma 0. B is a constant depending on the distribution and the morphology of the pores. Okay. So, if you plot this as a relative density, okay, the inverse of porosity, the relative density, then you get this kind of a plot. Once again, there is a lot of scatter in the data you can see, but one can get a more or less an exponential rise as a function of density. That means, as the porosity decreases, this is plotted as the relative density. So, it is the inverse of porosity, and show the fracture toughness or the flexural strength here, of course not fracture toughness, it is a strength, the flexural strength, bending strength increases as a function of density. Okay. So, higher is the density, higher is the strength, which is quite obvious, and it is not a linear increase. That is also have to remember that it is not a linear relationship, it is but a exponential relationship. Okay. So, when the porosity is very high, okay, the strength is quite low, but as you approach higher and higher density or almost theoretical density, it increases exponentially. So, that is a important observation, and that is an important criteria or important aspect of the mechanical behavior of porous materials. Okay. Of course, as you can see here, the plot has been given only from 90% or 85%, 85% to 90%, to almost 99% or so. So, this relationship is valid, basically valid at a porosity higher than about 85%. Okay. Below that, it may not be valid in that sense, because the other effects will come in. So, that was effect of pore size or pore porosity, the fraction. Here is another parameter, grain size. Okay. Most of the ceramics are polycrystalline nature, and grain size is certainly one of the parameters which controls the strength of the ceramic materials. In general, this is a kind of behavior. There is a different kind of slope. If you get if you plot strength as a function of root over grain size to the power half, okay, to a factor which is called G factor, or I think there is some, it is basically grain size. No, this is not the I think there is a problem there. It is basically G to the power half grain size. Okay. So, if you plot grain size to the power half root grain size, as the grain size decreases in this direction actually, and grain size in the top, as you can see, the grain size increases in this direction, the strength decreases. Okay. So, the finer is the grain size, higher is the strength. So, that is the normal thing. Once you get, you will find basically it is the intergranular fracture, it is the intergranular fracture which controls the strength of the material, and therefore, finer is the grain, the crack size is finer, and therefore, strength is also higher. So, that is once again a kind of empirical situation so far as the effect of grain size is concerned. That was a kind of theoretical curve, but in actual practice you get more or less the same behavior. This is for a particular material like spinel. If you plot the flexural strength as a function of grain size, once again you will get, as the grain size increases, the strength decreases, and there is a two different slopes. Up to a certain value of grain size, one slope, and then further there is a further decrease. So, at a smaller grain size we will get a lower slope, the variation is less, whereas in a larger grain size the variation is much faster, and you have a greater slope in this region. And of course, there is always scatter. The scatter is not exactly follow a straight line or a particular straight line. So, there is always a scatter around this particular behavior or particular line. Yeah, this is why the larger grain size may have a lower strength. The large grain size or intergranular cracks. Okay. The normal crack is intergranular, these are the grain boundary cracks along the grain boundaries or intergranular cracks, whereas if you have a very large grain size, you may have intragrain crack or sometimes called cleavage crack within the grains. So, this is possible when you have a large grain size. So, that is one of the reason why the large grain size will have a weaker property, or the strength will be less. The agglomeration followed by exaggerated grain growth normally leads to degradation of the strength, which we have seen earlier in our sintering discussion, that at a very high, after some time or after certain amount of densification, if you continue to heat for a longer time, you will get an exaggerated grain growth, okay, very close to the melting point, and that exaggerated grain growth will lead to a weaker material because of this intergranular or cleavage cracks, which is possible at higher grain sizes. Okay. So, this is one of the reason why higher grain size material will have a lower strength, and smaller grain size will have a higher strength. Of course, the so called metals and alloys, you have also a very similar effect. Higher grain size material has a lower strength, and smaller grain size material have a stronger or the higher strength, and that is also there. Of course, it is not the crack, it is primarily the primarily the dislocation, movement of the dislocation, which is important, and one gets so called the Hall-Petch ratio, a Hall-Petch equation, which is more or less the same what we have got here, the grain size to the power half dependence. Now, here is another important aspect of ceramics, which is not always true for other materials, other groups of materials like metals and alloys and so on. The volume size is the specimen size or the specimen volume. So, the larger specimens are expected to have larger flaws, which will cause lower strength, right. This is another very important aspect, once again primarily because the materials are brittle in nature, and it is the flaw size which controls the strength of the material. Larger, if you have a pre-existing larger flaws, they will be much more prone to failure, and therefore, if you have a larger specimen size, then that will have a lower strength, major strength will be much lower compared to have a smaller volume of the specimen from the same material. Okay. So, this is what a empirical equation you can write. The S is exponential V by V 0 sigma by sigma 0, again the similar expression what we got in the Weibull modulus, right. This is the basically Weibull expression. As the specimen volume increases or the Weibull modulus decreases, the survival probability decreases, and therefore, the strength also decreases, right. So, this is another aspect primarily because the materials are brittle in character, and it is the crack size which controls the failure mechanisms. So, it is some kind of a consequence of the Weibull modulus in fact. So, specimen volume also has a role on the accuracy of the measurement or the representative measurement or representative property which you are measuring. This can be shown here in a Weibull modulus, and there are the ratios of the component size to the test specimen size. Okay. That means, if you have the actual size of the specimen is larger, or out of that a small specimen, a small test specimen has been taken. So, the ratio of that actually gives you the volume ratio, volume of the test specimen to that of the actual size of the component, okay. And that is this stress ratio is actually a function of the volume ratio to the power 1 by m. M is once again the Weibull modulus, and then if you plot that as a function of the volume of the test specimen to that of the component, how much volume you have taken out of the total component or total solid for the test purpose, that has a relationship like this. The sigma, this particular relationship has been plotted here, and you can see if the modulus of the Weibull modulus is larger, then you will get the ratio very close to 1, okay, throughout irrespective of this test specimen, this volume ratio. Whereas, if the modulus is low, that means the spread is more, okay. The spread is more, and you have less representative measurement to carry out. Okay. So, volume also has a role to play. What is the volume of the test specimen you have taken compared to the component specimen, right. So, it is difficult to get a representative sample if you are talking about a large component. Large component means you have to take a large size of the specimen, right. So, that to get a representative property measurement. Now, those are some of the aspects of different aspects of the measurement, their reliability, and how to take care of the unreliability in terms of the Weibull modulus, and then the different factors which controls the property, which affects the property. Lastly, we will take a few other properties, that is, one of them is creep. Okay. Creep is a slow but continuous deformation of solid with time, particularly at elevated temperature. So far, all the properties we have taken, there was no effect of time. Time was not a parameter for our measurement or for our understanding the property. Here, for the first time, we are saying that with time there is a change in the property, or the change of expansion, right. That is what we call the creep strain. That means, at a fixed, from the Young's modulus we have seen, or the stress strain diagram which we have considered so far, that if the stress is constant, strain is constant. But here, even if the stress is constant, there is a strain increases. Okay. Its strain is no longer constant, it is a function of time. So, that is the continuous deformation or a time dependent strain. Time dependent deformation is actually what we know as creep, right. Usual creep curve, this is a typical creep curve of any material, in fact, whether it is ceramics or metals or alloys. Of course, all these deformation will take place. We have already seen that for brittle solids there is no plastic deformation as such. Plastic deformation can take place only at elevated temperatures, normally above half the melting point expressed in degree Kelvin, but for ceramics it is very closer to its melting point. There may be plastic deformation, and even if the stress is constant, there will be some amount of deformation as a function of time. So, depending on the time we allow the stress to be operative, there will be a strain, continuous rise in strain, and that is a typical creep curve. Okay. What is initially there will be a instantaneous deformation, and then the deformation will slow down or increase, sorry, not slow down, the rate will decrease, but there will be an increase of slope. Then there will be almost a kind of constant value over a time period, and then again there is a upturn. Okay. So, these three regions can be termed as the instantaneous deformation, then there is a primary creep up to this point when there is a faster rise, then there is a slowing down, there is a slowing down, almost the slope will go down, and then you have a once again a faster rate of strain or deformation, and that is called tertiary. So, it is primary, secondary and tertiary. Okay. So, these are the three regions of a normal universal creep curve, and this of course is dependent on the temperature or stress you apply, because there is always a constant stress. What is happening, the deformation is taking place under a constant stress, and that constant stress can be varied or the temperature can be varied. So, the creep curve will also change, the nature of the curve will also change. If the T, that is the temperature, is less than 0.4 of Tm, the melting point, so where creep is negligible. So, there is a hardly in deformation as a function of time, or increase in deformation as a function of time. So, there is a constant strain. If you increase the temperature or the overall stress under which the deformation is taking place, then there will be a change in slope, and this will be the type of curve which, compared to this, ultimately you are getting a very similar curve like this, and that is a kind of universal curve which we get only at a higher temperature like T3. Here T3 is more than T2 and T1 still more than T1, or at a higher sigma with the stress which we apply, sigma 3 or sigma 2 and sigma 1. So, sigma 2 is greater than sigma 2 and which is also greater than sigma 1. So, this is the behavior of any material, and including ceramics, and particularly at higher temperature. Well, this is what we call the power law creep. The expression is sigma dot, which is d sigma dt equal to gamma into p to the power sigma to the power p. So, p is the creep law exponent with a value of about 1 to 10, varies between 1 to 8, okay. And gamma a temperature dependent constant. So, this is what we call the creep power law of creep, okay, or a steady state creep. In fact, this is a kind of steady state creep here, okay, the secondary creep. Now, there are different mechanisms of this creep. I will just simply finish this with this mechanism. Okay. It seems the time is up. Just very quickly, it is a diffusion creep, that is one of the mechanisms, and then you have two other mechanisms. One is called viscous creep and there is called the dislocation creep. So, there are three different mechanisms. Maybe we will discuss little more about these mechanisms in the next class. So, thank you very much for your attention. Thank you.